This is an introduction to enolates, which appear in chapter 21 of the Klein text. This is the third carbonyl chapter. So first we had reactions of aldehyde and ketone carbonyls. Then we had reactions of carboxylic acid and derivative carbonyls. And now you might be wondering what's left. Well, this is what's left. And I decided to do this little screencast because I talk about some of the information that's here a little bit out of order when I talk about it, and I'll show you when that comes up. Just to me, it makes more sense to give you kind of the whole story rather than some of it and then more of it. So the first thing is that the alpha position relative to the carbonyl, so here's the carbonyl, here's the alpha position, is kind of acidic. We're not talking about majorly acidic. So the pKa of this carbonyl is about 20. So it's not even as acidic as a phenol or a thiol, but it's kind of acidic. And so if we use a base, and I chose not to put charges here, we can remove this hydrogen. And the reason why this compound is acidic at all is that its conjugate base is stabilized by resonance. So we can write a second resonance structure where we delocalize the negative charge out onto the oxygen. And this would be the quote-unquote better resonance contributor because the negative charge is on the more electronegative atom, which is oxygen as compared to carbon. This species is known as an enolate. So that 8 ending, which generally implies some sort of an anion. So we have that 8 ending. And these things react as nucleophiles. So if something reacts as a nucleophile, that means it's going to react with an electrophile, again, whose charge I really didn't specify. And this enolate is what's referred to as an ambident nucleophile. Amba meaning more than one, like amphibian or ambidextrous. And so they can either react as carbon nucleophiles or as oxygen nucleophiles. And it turns out in almost every instance, they react as carbon nucleophiles. So if that happens, the electrophile gets attached to that alpha carbon. And the electrophiles that we're talking about here are the alkyl group of an alkyl halide, halogens, or carbonyls. So we're going to go back and revisit those last 2 chapters because some of these carbonyl compounds are going to be aldehydes and ketones, and some are going to be, esters. You can't really make an enolate out of a carboxylic acid because you'll pull the acidic proton off. And some of the other ones, the other carboxylic acid derivatives are pretty reactive. And I guess you could do it with an amide. So if this compound reacts as an oxygen nucleophile, you'll get this. And typically, this is something that happens only with one particular electrophile, and that electrophile is hydrogen. So all this happens under basic conditions. Under acidic conditions, or basic conditions, but acid or base, you can form an enol, and you might remember enols from when you learned about the addition of HOH across carbon triple bond carbons, that the initial product that you got was an enol that wasn't stable relative to the ketone form, so you did this tautomerization. Well, it turns out that these enols can also react as nucleophiles, and they'll react with an electrophile to add the electrophile on that alpha carbon. The only reaction that we'll look at that involves an enol as opposed to an enolate is halogenation. Everything else will be delving only into the enolates. Notice that if you compare the enolate to the enol, especially if you, you compare this form of the enolate to this, it's pretty easy to see that what you have here is an acid conjugate base pair. So let's talk a little bit about acid-base stuff. So if you have an acid-base reaction, you have something that's acting as the acid, something that's acting as the base. And so what we're trying to do here is remove a proton, an acidic proton. So that means we're going to worry about how acidic the alpha hydrogen is and how strong of a base do you need to remove it. So I got these out of the pKa table that I have online. There's one that I added that wasn't in there. I added this one. So we have a pKa of 25 for being alpha to an ester carbonyl, 20 for being alpha to a ketone carbonyl, 17 for being alpha to an aldehyde carbonyl. And again, all of these enolates, resulting enolates, can be resonance stabilized. Then when we move into the realm of the 1,3 dicarbonyl compounds, so we're calling them that because the two carbonyl groups are 1, 2, 3 versus each other. 1, 2, 3, 1, 2, 3. Or you can think about it, you have a carbonyl, a non-carbonyl, and then another carbonyl. So with these compounds, notice that they are significantly more acidic. So if we compare the diester to the plain ester, there's a difference of about 12 pKa units. Likewise, if we compare the monoketone to the diketone, there's a difference of about 11 pKa units. And the reason for this is that the enolates of these are doubly resonance stabilized, so you're able to move the negative charge onto either of these two oxygens. In order to be able to do that, though, you have to remove, to make the enolate, the hydrogen on the carbon that's directly between them. So clearly, these are going to be more acidic than the equivalent versions of these. So as you may remember from second semester general chemistry, if you have a proton transfer reaction, and I wrote one exactly like the ones that they write in Chem 12 a lot. So we have an acid HA reacting with a base to give you a conjugate base and a conjugate acid. And from Chem 21, remember that if the acid is stronger than the conjugate acid, so you're going from the stronger acid to the weaker conjugate acid, that's a favorable process. Going from weaker acids or bases, going from stronger acids or bases to weaker ones is the favorable pathway. So this is going to have an equilibrium constant greater than 1. Acidity and basicity are thermodynamic properties because they involve equilibrium. So therefore, we're going to be talking about equilibrium constants, not rates. Conversely, if you reverse this reaction, or if you just go from the weaker acid to the stronger conjugate acid, that's not thermodynamically favorable, and your equilibrium constant is going to be less than 1. That's really what you need to know. If you want to get a little mathy, you can use this equation, which comes from the law of multiple equilibria. It's not something that's based on the mass action expression. And so the K for this overall proton transfer reaction is going to be equal to the Ka of the compound acting as the acid divided by the Ka of the compound acting as the conjugate acid. Students sometimes don't like this equation, perhaps because it might involve math, but also because they keep saying, but when you write a mass action expression, the product is up here. We're not writing a mass action expression. Again, this can be derived from the law of multiple equilibria, something that I would do if this was Chem 12, but I'm not going to derive it for Chem 22. Remember that the Ka is equal to 10 to the minus pKa. So if you have these nice whole number pKa's that I provided to you, it's pretty easy to get the pKa. If you're ever in a scenario where you do have to do something quantitative with this and you can't remember what the numerator and the denominator are, if you remember that you divide one by the other and you remember what has to be true for K to be greater than 1 versus less than 1, you can work that out. So to answer the question, how strong of a base do you need? Kind of the glib answer is you need a base whose conjugate acid has a pKa that's greater than the pKa of the hydrogen on the alpha carbon. So in other words, the conjugate acid has to be weaker than the acid. And ideally, you want that to be by more than about 4 to 5 pKa units. If you have a reaction with an equilibrium constant of, say, 10 to the 5th or greater, it generally goes to completion. That assumes that you want to convert your carbonyl compound completely to the enolate. And it turns out that you don't always want to do that, something we'll get into a little bit more as we get into the chapter. So I worked out a couple of examples here. They're kind of running into each other, but I guess we'll live. So with this first example, we have ketone acetone reacting with hydroxide to give you the enolate of acetone and water. Well, the pKa of water is 15 to 16, depending on whether you believe the general chemists or the organic chemists, and the general chemists are right. So we're going from a pKa of 20 to a pKa of 15 to 16. We're going uphill energetically, and if we calculate the K is equal to about 10 to the minus 5th to 10 to the minus 6. So what we have here is a reaction that hardly occurs at all. If we get out the big guns, so this is a base called LDA, where LDA stands for lithium diisopropylamide. You're never going to be able to read that once I condense this back down. And this is the anion of an amine. So we think of amines as being bases. So this is the conjugate base of a compound that's way more of a base than it is an acid. And so if you look, the pKa of its conjugate acid is 36. So that's going to be a weaker acid than pretty much anything. So will LDA completely and irreversibly remove this proton? Yes. And the K for this is about 10 to the 16th. Yes, it does that. So if you're in a situation where you want to convert a ketone completely to the enolate, LDA is something that you can use. It'll turn out that in some reactions we actually want to have significant amounts of both the original carbonyl and the enolate that's its conjugate base, and in those scenarios hydroxide is the better choice. But now look what happens if we have one of these more acidic 1,3-dicarbonyl compounds. If we react that with hydroxide, conjugate acid is still water. Water still has a pKa of 15 to 16, depending on who you believe. So now we're going downhill energetically. This is going to have a K of 10 to the 6th to 10 to the 7th, and so this would go to completion. So you could take sodium hydroxide or sodium methoxide or something and add an equivalent amount to one of these 1,3-dicarbonyls, and it would convert it completely into the enolate. So then I just made a couple of notes down here. Sometimes you want complete conversion to the enolate, sometimes not. And I also noted that there's a chart of bases that you can use to make enolates. This is based purely on equilibrium factors, and that's on page 961 of the Klein text. So now this part up here, the book kind of addresses at this point, but the part on the Regio Chemistry, not so much. It doesn't address it until later in the chapter. But I think as long as you're talking about the different bases, you may as well just go on and get this done, and then it's done. So aldehydes can only make one enolate. Esters can only make one enolate. 1,3-dicarbonyl compounds effectively only make one enolate because there's only one carbon that's alpha to both carbonyls. However, ketones that aren't symmetrical can make more than one enolate. So for example, and this is kind of a classic example, if we have this compound, this 2-methylcyclohexanone, this compound can make two different enolates. So we can either remove this green hydrogen on the right side of the molecule to make the green enolate, or we can remove one of these two hydrogens, purplish hydrogens, on the left side of the molecule, and we can make this enolate. And so that's the Regio chemistry. Do you put the negative, do you remove this hydrogen or this hydrogen? So we can look at these in turn. We'll start with the one on the left. So we have two purple hydrogens versus one green hydrogen. So if you had a bag of marbles and you had twice as many purple marbles as you had green marbles, and you just started pulling marbles out of the bag as fast as you could without looking, you would end up with more purple marbles because there are more of them, unless somebody stacked the deck by putting all the purple marbles in the bottom or something like that. Or they were different sizes. But, assuming all other factors being equal, you would end up with more purple marbles. And so for a reaction that's based totally on the rate and is not reversible, we're going to get more of this compound where you could remove one of two hydrogens to get it versus one of one. So this is statistically likelier. However, it's less stable. If we compare this to this, and we look at the resonance contributor with the carbon-carbon double bond, and we apply our vast knowledge of carbon-carbon double bond stability, this double bond is less substituted than this double bond. So this is less stable. So this is faster but less stable. And we call this the kinetic enolate, sort of like we talked about the kinetic versus the thermodynamic products of conjugate addition. So if we want to get this kinetic enolate predominantly, there are two things that we can do. We can do the reaction at low temperatures, because at low temperatures it's going to make it harder for the reaction to reverse. And we can also use LDA. So LDA is kind of bulky. That's the one we just talked about up here. So it's kind of bulky with those two isopropyl groups. And that's going to make it a lot easier for that LDA, which is a little bulky, to grab one of these two rather than the more sterically hindered one. So if we want the kinetic enolate, LDA, low temperatures, students sometimes wonder, why the heck do we have minus 78 degrees Celsius? That seems like this totally random number. It's not totally random. It turns out that if you make a bath, and you've all made ice baths, but if you make a bath using dry ice and acetone, that the temperature you reach with that dry ice acetone bath is minus 78 degrees. So there you go. On the other hand, if you let this reaction reverse and go back and forth, oops, that's not what I meant to do. I always do what I don't mean to do. I think I'll just not get fancy with the colors. If you let this reaction maybe be a little more reversible, then you're going to get more of the more stable but slower to get compound. So if the reaction is allowed to go back and forth, you're going to get more of the more stable product eventually, so-called thermodynamic enolate. And for this, we're going to use a petite base and warmer temperatures, because that will promote reversibility. And so we can make a little chart, reaction coordinate diagram. And so the kinetic product, the purple product on the left, has a lower activation energy. It's faster to do that, but it has a higher energy. The thermodynamic product, since the other one has a lower activation energy, this one must have a higher activation energy, but it is more stable. So if the reaction only goes forward once, it's a lot likelier that you're going to get the purple product compared to the green product, the thermodynamic product. If, on the other hand, you let this reaction go back and forth several times, over time, you'll end up with more and more of the thermodynamic product. So if you think about this, let's say you did the reaction forwards and you got some kinetic product and some thermodynamic product, even 50-50. Of these two, it's going to be easier for the kinetic product to go back the other way, because the activation energy for it going backwards is lower than the activation energy for the thermodynamic product reversing back to reactants. So more of this is going to reverse. So this is going to hang out, let's say. More of this is going to reverse. So now when your kinetic product has gone backwards, When it goes forwards, it's going to sort itself out so that you're going to get some of each of these two products based on the relative activation energy. But since you started with, you lost more of your kinetic product, and when you went back over time, you're going to end up with less and less kinetic product and more thermodynamic product. And then I have the note here, I already said this, that most of the reactions in this chapter that we'll talk about are under basic conditions, and therefore they involve enolates rather than enols. So we'll see a lot more enolate chemistry than enol chemistry, again, except